And to do this, I am going to rewrite the cosecant as 1 over the sine. So this right here is equal to the derivative with respect to theta of 1 over sine of theta. And now I have a quotient. So the derivative of the numerator here is 0 times the denominator minus the derivative of the denominator, derivative of sine is cosine, times the numerator, all divided by sine squared theta, right? Quotient was that square at the bottom. All right, 0 times, that's gone. So I end up with a negative fraction that is cosine of theta divided by sine squared. And we all know, based on the trig identities, these functions are very inbred. So there's a good chance I can rewrite cosine over sine squared. So I'm going to mess around with doing that now. We still got that negative hanging out front, so I'm just going to leave it there. And then I'm going to rewrite this as cosine of theta over sine of theta times sine of theta. And then I'm just going to make a little observation here that if I take the cosine divided by the sine, that's cotangent. So I'm going to get negative cotangent of theta from that part. And if I take 1 over the sine, well, I know that's cosecant. So that would be another way to state this derivative. And usually the cosecant is written first for some reason, but it doesn't really matter. But it's the opposite of the cotangent cosecant. Now I'm going to forego proving the others. You could easily do that based on the 2 examples I just did about tangent and cosecant. Just going to list out all the trig derivatives. So we have the derivative with respect to theta of the sine of theta is the cosine of theta. We now have the derivative of the cosine is the negative sine. We also have the derivative of the tangent is the secant squared. And then, although I didn't show it, I'm just going to state it, the derivative of the cotangent, which can be calculated in a similar way that we did the tangent, is equal to the negative cosecant squared theta. We just figured out that the derivative of the cosecant is the negative cosecant theta times cotangent of theta. And similarly, the derivative of the secant is equal to the secant times the tangent. You should see some patterns here. So at least 3 patterns jump out at me here. Pattern number 1, I think, is of some importance, is that anytime you take a derivative of a cofunction, cosine, you get a negative, cotangent, you get a negative, and cosecant, you get a negative. So all the derivatives of the co-functions are negative. At least have a negative multiple up front. So that's interesting pattern number 1. Interesting pattern number 2 is the way these functions switch between a function and its cofunction, right? So the derivative of the sine is its cofunction, cosine. The derivative of the cosine is its cofunction, cosine. If you don't remember what a cofunction is, a cofunction happens when you switch your perspective inside of a triangle. So in the right triangle, if we say this is 1 right here, and this is theta, then this would be the sine of theta, and this one here would be the cosine of theta. However, if you change angles, if you instead decide to look at this angle up here, alpha, then sine and cosine switch. This becomes the sine of alpha, and this becomes the cosine of alpha. It's supposed to be an alpha. And alpha and theta are related in that they are 90 or pi over 2 in their sum, right? They're complementary angles. So that's the idea of how cofunctions are related. They switch when you switch the angle you're looking at in the right triangle. So some other interesting cofunction things are derivative of the tangent is the secant, and the derivative of the cotangent is the negative cosecant squared, right? So those two have an interesting relationship. And same here, derivative of cosecant is negative cosecant cotangent, and correspondingly derivative of the secant is the secant times the tangent. So they just swap functions with cofunctions, positive with negative. And these are definitely things you should remember, at least the sine and the cosine. You better have those down there. One other cool pattern, take a look at, and then we'll move on to some more fascinating problems. But I think this one is pretty awesome. If we say that f of x is equal to the sine of theta, then we know its derivative, f prime of x, is equal to the cosine of theta. And if we take the derivative of the cosine, that would be the second derivative of the sine, my original function. So f double prime, derivative of the cosine is the negative sine of theta. And if I just keep taking derivatives, so the third derivative of the sine, well, the derivative of the sine is the cosine, but we got that negative hanging up front. So it'll be negative cosine of theta. And then if we jump to the fourth derivative, which usually we'll use a Roman numeral for typically, derivative of the cosine is the negative sine, but I already have a negative out front, so I get negative of a negative, and I get the function I started with, sine of theta, back. So we have this cyclical pattern here in terms of repeated derivatives with the sine and the cosine. So there's that cycle of 4.